New York Haskell Users Group. I'm really excited about this turnout. I know that this room is full of a lot of people that have some experience in Haskell, and I believe some that are just starting out and want to learn more. And so we're going to try to be a group that services both, and that's why we have 2 talks today, and on other days we'll try to mix it up and have a bit of everything. And yeah, I won't get too much more. Plans will develop, but I'm really excited, and I think I've got my name is Gershom Bazerman, by the way, and there's a great core team of organizers, another who will be speaking tonight, and some others we'll introduce later. So we're going to be able to keep this group going, and I'm sure it's not going to die on the vine. What else do I want to say? I want to thank Pivotal for the meetup space, for providing the food, providing the refreshments. Thank you, Pivotal. Couple things about the space, if we keep using it in the future, is just, everything outside of this area is Pivotal's area, so we're supposed to combine ourselves here, which is, a very nice area. If you want Wi-Fi, on the walls, there's these little signs, and they list the net and the password, so if you want to dial in for any reason, take advantage of that. We have swag, courtesy of Boston Haskell. We have stickers. They're transparent. You can stick them on things to show how hardcore you are. Feel free to come take some. We're probably going to have more made later, so that's cool. What else? Oh yeah, I just want to do a straw poll of the room. How many people have installed a Haskell compiler and written a couple programs with it? Okay. All right. How many people feel like they've written one program that they can actually use in their life in Haskell, like in a real program? At least one. One or more. Okay. How many people feel like they know what a monad is? Okay, wow, this is really good. This is much better than I had feared. All right. How many people, sorry, now I'm going to get silly. How many people think jQuery is a monad? Beautiful. All right. Okay. We'll go back to it. Okay. All right, so let's just get started. So hopefully, it looks like the room has actually got a bit of a higher level than I thought it might. So we'll let Oz take it away. Ozgun's at Sioux Stone. He'll tell you about what they do. And he'll show us some of the libraries he's built and some of the ways he does cool stuff with them.
All right. Hi, everyone. This is Oz. I'm going to talk a little bit about, I guess, some practical things that you can start, doing with Haskell. I myself come from a very practical background, so certainly interested in the philosophy and the academic parts of it too, because it expands the mind. But I'm definitely interested in, doing useful things with Haskell. I myself started about, I'll say it, I guess, in a second too, but I started about maybe 4 years ago. And ever since, I've been using Haskell pretty intensively, so it's been a busy 4 years. And I'll just tell you about how I started and how I think you can, if you're interested, start in your daily work too, and hopefully it'll grow from there. The point of this talk is not really to really teach the language or anything like that. It's too big a language to teach this quickly, and there are very good resources way beyond what I could do here. But I guess before I start, just a little bit about myself. I'm a mix of, I guess, engineering and a little bit of business. I have been a management consultant for, I guess, 4 or 5 years, but definitely with a strong flavor of analytics, which gave me ample opportunity to do data processing and things like that using Haskell. As I'm sure, like many of you, I've been coding forever, and then, like I said, Haskell for 4 years. At least. I used to use Ruby and Python for everything. I did a pretty big commercial project using Ruby on Rails a while back, so at least I got that perspective. I really started with Haskell using, I started using Haskell with simple analytical problems, like I have this data set and I need to make a few fixes on it. How do I, could I use Haskell for this and maybe get started? That really was my starting point, and I think it's a very good one because it really eases you into the whole language. I founded a company about a year ago now, and we use Haskell for essentially all technical aspects wherever we can. I happen to be a core contributor to the Snap framework, which is a web framework, one of the major ones, at least, in Haskell. And I've also released a number of libraries on Hackage over time. There's a few more waiting to be released, hopefully, one day. So I guess this talk, as Gershom was just saying, is meant to be kind of a beginner's talk. Nothing too advanced here. The point is to hopefully motivate some of you to give Haskell a try for a serious project soon. Definitely we'll try to point at some simple, I guess, things that hopefully will resonate with some of you. Depends on, I guess, where you're coming from as well. Obviously, it'll give us a chance to talk about Haskell syntax as well. So if you have no clue what Haskell is, then we'll walk through that as well. And the rest, I guess, I talked about. So already a few people asked me why I chose Haskell for my company. And more generally, each one of these talks must have a page that talks about why Haskell is so good. So here's, I guess, my personal take. I'm by no means, I'm not like crazy about Haskell or anything. I have very practical reasons for using it. So I guess a few of them that I can think about off the top of my head are, first of all, the type system. Once you get used to it, it's really great for clarifying your thoughts. It's really expressive, and you almost start designing whatever you're trying to solve in the type system itself. So I guess compared to Python, for example, there you would just write an imperative, do this, then add to this, do that, add to this. That's how you would start. Whereas in Haskell, you really start with what is it that I'm trying to do here? What kind of a, let's say, transformation am I seeking to achieve? So that's, I think, number one, probably emerges over time. More practically, thanks to the type system, you catch errors early on. So if you have a serious project, I think the nice thing about Haskell is you can be as high level, if not higher, than a language like Python, while also retaining the extreme type safety. Yes, there's a few things you can't do in Haskell, and you can in Python, but I think Haskell allows you to do many, many really practical things while still being very safe. I've found that purity is a huge win. I guess if you don't know what this means, it just means that you can't do I/O everywhere in your code. You have to do I/O in sort of a restricted section, and then your logic has to be sort of pure mathematical, equationally transparent. So it's actually a huge win because you can write code today, you can come back to it 8 months later and have confidence that it's not doing anything funky. You can actually teach yourself back what you wrote 8 months ago, and you can make tweaks, deploy that code knowing that you likely didn't break anything. Like I said, you can set a very high level, that's fine. Testing is really, I was talking about this to a couple of folks here, it's really amazing. If you don't know Quick Check, you should look at it. It's almost magical the first time you use it. It's great. We could talk about it after if you're interested. So multi-core concurrency is unbelievably easy. Really, once you use Haskell for a few years, it's just funny. You go back to Python, you're like, what? I can't just fork a process and have this run in the background and without worrying about anything, and you're like, no, I guess have to figure something else out. With Haskell, it's fire and forget. Just fork something in the background, it'll run. It's really great. And there's all kinds of parallel algorithms and research in that area that that promise a lot. So I'll talk here about data processing, and what I mean by that is, I guess first of all, a bunch of simple tasks. I'm not sure if this is the kind of thing you do a lot, but I've had to do a lot of it. Things like you get a CSV extract from some legacy database somewhere, and you need to do something with that data, and it's just really messy. It uses tilde as the separator character. It's all uppercase where it shouldn't be. It has month names in like text as opposed to a number, and it's like constant width, so it'll screw up your MySQL if you just import it. So you just have to clean it up, or maybe you're tying into a sort of an API somewhere, and it gives you JSON, which is great, but it's not really great for analytics. If you want to actually analyze that data, there's not a lot you can do with JSON at this point. So this is maybe some simple use cases. Obviously, the more complex parts, whatever, you can do really, really fancy things. And I'll try to hopefully hit some of each category today. So I guess my point in the second part here is that you can use Haskell to really build command line utilities, for example, which is a very easy thing to do, that just automate parts of your life if you do a lot of data crunching. Okay, so just getting started with Haskell. So Gershom just asked, I guess a lot of people did this, but it's actually fairly easy. You just go download Haskell platform. Comes with all the basic things that you need. Then you just need to do a little Cabal update, just sort of refreshes your repositories, and then you can just install whatever package is available on Hackage. I think last time I checked, we had something like 3,500 different packages, maybe more. I think, Doug, you looked at it recently, but lots and lots of packages on Hackage for all kinds of different things. And I've found that one of the really good things is, because of the type system, if a package has actual documentation, meaning it actually compiled, it may not be great, but it'll at least work, because there's something that sort of checks that it is working, which is something I used to like with Ruby, for example. You download a package or a gem, really no idea if it's really a good library or not. And here are some, I guess, learning resources. I'll maybe post these slides later if you're interested. This is how I sort of learned them myself, among other things. But okay, so a few sort of things about Haskell to keep in mind as we talk about all this. It's a purely functional language, which basically means you can't do I/O everywhere. You have to plan your code so that you have your logic in one place, and then you kind of tie it with the outside world. So if you're wondering why we don't just sort of open a file in the middle of a function, that's why. It's non-strict, so you can't really, or it's lazy, I guess. There might be a little difference there, but you don't really control evaluation. So you just tell it what things are, and then it decides when to actually evaluate a function. Which is usually it's good, but sometimes it's a little confusing because you're like, okay, I don't know when this actually gets executed and in what order. But for the most part, it's not a problem. It's statically typed, that's obvious. It's strongly typed, so it will do no implicit conversions for you. You have to explicitly convert or typecast anything you want, if you ever need that, and you do typically. It compiles to native code, which is pretty actually good because you write a program at a pretty high level and it really just compiles down to the machine, and it really performs pretty fast. The GHC compiler is the standard, so if you're looking at different compilers, I mean, in general, that's what you use for your real-world projects. I know some companies have their proprietary compilers written, but that's all private, so we don't use that. Like I said, the runtime system is really good at sort of concurrency. So any kind of thing you want to do in parallel, it'll take care of all that itself. And there's a bunch of language extensions that if you ever see them or hear about them, they're pretty commonly used to make things more expressive. Sorry to give you a long list here, but I guess I figured with a sort of possibly beginner audience, if you knew nothing about it, then some things might have looked a bit funny if you don't have this. Okay, so with that, I guess we'll just dive in, and I'll talk a little bit about syntax as I go through this. Sorry if this is really trivial, and sorry if it looks like a lot of code all at once. But here's a simple program that could actually parse a CSV file. So CSV files, as you know, comma-separated values. You really just take tabular data, you just sort of create a table with it, separate with commas, and you just have new lines, I guess, delimiting different rows. So I guess a few things here. I wonder if I could point this way. Yeah. So I guess you start a program with sort of a module main that sort of says that this is going to be an executable, and it's, let's say, the main part of the program. Yeah, import some, let's say, string-related libraries. That's fine, nothing fancy there. So here already, I guess, you start thinking a little bit about types. And in Haskell, probably the biggest thing is types are not things that are really sort of adding friction to the system. So they don't really slow you down, or they're not necessities. You really use them because you want to sort of design this expressive thing that's almost self-documenting. So in this case, we could say that a field in a CSV file is itself sort of a string. Then here we say a row is a list of fields. So now I have several of these, I guess, strings, and that makes up a row. And then again, naively, I could say that a CSV, the whole thing, is really a list of rows. And that's it. Sort of, that's, I guess, my very simple design for a CSV libraries interface. So when you parse a CSV file, all you're really doing is you go from some blob of string into a better structured CSV file that's a list of lists, and you can manipulate it and do something with it. So that's I guess, the fundamental idea. Now, how would we actually do it? Actually, all of that is really this one-liner here. So I guess I'll just walk you through it. In Haskell, a function application is just, I guess, just space. So there's no parentheses or anything like that. So when you say parse CSV string, this would essentially be, this is the function, this is its first argument. By just putting them next to one another, you just sort of apply the argument. I guess one part I maybe skipped over is how to read this type signature here. And I guess just so I know, how many people here have like no clue about any of this? Like, do you know does anybody not know what a type signature in Haskell is? Okay. Sure. Okay, so I guess I'll just mention it quickly then, but good thing I guess almost everyone knows it. So this basically means that I have a function parse CSV. When given a byte string, it will produce a type of CSV. So it just kind of all the way until the very last one you see are arguments, and then the final point at the end of the rightmost arrow is the thing you get as a result. Some other signatures might have several of these arrows. It just means you have several arguments. You just keep giving more arguments to it. But type signatures are almost documentation for Haskell folks. You just look at the signature and essentially tells you what the function does. So here what we're doing is, as the parse CSV function, we're taking a string, and we're giving that string to this function here that we construct. And this we basically read like, I guess you would in math. So there's this first function here, so going from right to left, it's basically your function composition. You take the string, you apply first a function called lines, which really takes the string and sort of chunks it into pieces based on the new line characters. So it will take a string and turn it into a list of strings. At this point, there are, I guess, blobs of rows. You essentially sort of took a blob and turned it into sort of individual rows. And then you take each such row from that initial application, and you split it on a comma. And then the map here is, I'm sure it sounds like everybody knows this already, but the map here basically says, take this function and apply it to every element of whatever list you have to the right of it. So essentially, take the blob, turn it into rows, take each row, turn it into fields. And as a result, you basically have your parsed CSV. Now, you might have noticed already that this is all a pure computation, meaning there's no I/O here. It doesn't actually read anything from a file. It just does the reusable piece, which is taking a blob of string and turning it into a more reasonable CSV, which is a very common pattern with Haskell. You design sort of like the core of whatever you're doing as an independent piece, and you can use it in many places. Now, you can use that, you can open a file, which is what we do here. You can read from a file, get that blob here, and then apply the parse CSV to it here. I could read it from the network. I could download a file from the internet and apply the function. So that's, I guess, already beginning to, what's emerging is that whole reusability that people often talk about in Haskell. It's a very simple example. So I guess any questions so far? I'm hoping it's pretty straightforward. Okay. So, but obviously, this is a very simple design. You might say, okay, what if I want to use not a comma, but a tilde as the separator? What about text quotation? What if I have different line endings and all kinds of things? Then I would say, I guess this was a good, useful exercise, hopefully, but actually go use a CSV library. And a few years ago, there actually wasn't a very good one. So for my work at the time, I ended up writing a first version here myself. But now there are others, depending on which API you prefer. I guess I'll pick mine for the rest of this presentation just because I know it. But my point there was I needed something that could operate in constant space. I wanted to give it maybe like a 10 gigabyte file and have it actually fix every row of it without spending like even more than a few megabytes of RAM. And I wanted it to be fast, and it needed to be very flexible so that I could specify different delimiters, different options for it. There was nothing at the time, so I ended up creating one. And if you use one of these libraries, obviously the job becomes really simple. You just import the library, and then you say, read the file for me. So you say read CSV file. It takes a settings object and an actual file path, which is, I guess, a path on disk or somewhere. And then it'll just return it as a list of dictionaries. And here the dictionary it's just a map of text to text, which is, this is the column label and this is the column value. So you can imagine each dictionary being one row, and if you read the list of it, you'll just get many rows. Now, obviously the point is if you read the whole file at once here, you just lost your constant space guarantees because the file might be big. That's not the point here, but just to, I guess, illustrate the point. Now, I guess another thing that I personally like about Haskell is it just makes everything very clear. So I guess there's no point in getting into a sort of a flame war with comparing to other languages. But I do like the fact that I can when designing an API, I can create sort of a very sort of by itself defined record that says, okay, this library takes something called CSV settings. You can define the CSV, the input separator, the input quotation character. If I'm outputting ever, I can specify if text should be coded, and I can specify my output sort of separator. And this is all defined as its own object, as its own data type. It's not a full-blown object. It just keeps the data. It's very clean, and also very obviously communicates what I guess this library does and what options you can provide to it. I do like that it's very clean, and I quite often forget my own libraries, but I can just look at easily the documentation. Just seeing the type signature for this record, I know exactly what I can supply to this thing, and that I like. And then I can always start with some default settings and just tweak the little bit that I care about in such a design. Okay, so I guess getting a bit more practical, because my hope and my point here was hopefully you'll leave today and maybe a few weeks down the line, if you're interested in Haskell, you'll run into a simple problem and you're going to say, you know what, let me try to solve this using Haskell. So let's turn, I guess, these couple of things into an actual executable that honestly I know would help a number of people. So the problem here is, like I just described, data from legacy systems are is quite messy when you get it, and you need to clean it up before you can do anything with it. Here's an example. I actually typed this up myself, but believe me, this is based on real experience. So you get, let's say this is, I don't know, I guess maybe a car dealership, some information backend. So I hate this thing. Anyways, you have these constant space delimited, I guess, fields. You have the car name here, and then it has like an arbitrary number of spaces. Then it puts a tilde as the separator. Then I guess you have something like maybe it's price. But again, you have a bunch of spaces to its right. And then you have another, maybe this is the inventory count, but it has 2 zeros preceding it, which might screw up your downstream system in certain cases. And then you have a bunch of spaces again, and then you actually have another field here that doesn't have a value, but it's there. So this is quite messy, and believe it or not, I've personally seen many, many data analysts who take this data, create first a SQL table with all strings as fields, dump it in there, and write a bunch of ad hoc SQL queries to actually clean this up. And I'm being nice here because this thing is like 5 fields. I mean, usually these things are like 137 fields, and you're just good luck. I mean, you give it to the analyst, it takes them maybe a week, and they come back, and here's the data set, only to realize you didn't even need the data. So here's maybe the mission for us here. Let's write a simple command line tool, and this will be very simple, but I'll show you maybe a next step improvement. Let's be flexible in the field separator, so we can tell it use tilde, please, and maybe don't have any quotation characters for this file. Be able to operate on really large files, and just kind of go over the whole set, just strip all the white space, make it clean for me, so I can just dump it in the SQL database. So usually when we do these things, and maybe I think this is something different about Haskell. I don't remember anymore how I used to think before, but usually you start with the types. You just kind of say, you sit down, okay, what is it that I'm trying to do here? Without even implementing any functions. At a very high level, you think to yourself, okay, I guess I will need a function at some point in this module that will take some CSV settings that I'll specify, a file path as my input. Here's where the input file is. And here's where the output file is, and it'll do its thing, and hopefully the output file will be clean. Okay, so then you just write that type signature, and that already is almost like some documentation for you as you think through this. Then you say, okay, I guess I'll need something like a fixed row function. It'll take a row, it'll do something with that row, and it'll either decide that row should be filtered out, so eliminated. That's why the output is a list of rows here. So it might choose to emit an empty list, in which case I guess the row was bad, maybe it was blank, so you just kind of filtered it out. Or maybe you decided that from that row, you actually need to split some field into multiple subfields and emit multiple rows at once. So all of that, you basically, all that thought, just by one signature, you've already sort of expressed it. And then you say, okay, at the lowest level, I'll need a fixed field function that'll just take a text. It'll do something with that text and clean it up, and hopefully, and that's it. So I mean, already, at least this is how I usually design it, and I think this is a lot of Haskell folks. And you know, it's pretty clear what you need to do. So here's a very, very simple implementation. You could say my fixed field function is just strip. It'll just strip out the white space, so make sure that the field itself is clean. This is a library function somewhere, so no need to re-implement it. It's already there. My fixed row function, let's make it slightly more complex. So, and here we can do something called pattern matching. I guess I'm assuming a lot of people know it. But here, what it's saying is that there are two alternatives for fixed row. So alternative 1, if it takes an element of 1, so it really, you gave it a row that had a single field, and that's all it had, then it checks to make sure that after fixing that field, the field is not empty. If the field is empty, so it fixed the field, the given field, and if it's empty, it will just output empty, sort of empty list for its own output, which basically means it outputted sort of nothing, which means eliminate that row. Essentially translates to, if the row was totally empty, just filter it out. We don't want to have any junk in our database. If it was anything else, so if it wasn't empty string here, if it was anything else, then fine, just output that as a one element list. So probably meant that my row had a single field, and that was fine. Sorry if you guys can't see it from there. And then for the other cases where the given row has more than one field, because this was the only case where there's one field, and now pattern matching sort of goes from top to bottom, then you say, okay, take that list of fields, apply fixed field to each element, and return that as a single element list. Again, because I have to return a list of rows. So this is very simple. I mean, this by itself, it'll just strip all the white space. It'll eliminate totally empty rows, and then otherwise it'll just make the fields a bit nicer. Very simple implementation. Well, I mean, I guess what else could we do? Well, theoretically, if you go back to just the type signatures here, you can basically, take any of these functions and make it arbitrarily complex to suit your needs. So for example, while fixing the row, we could choose to take a field there. Let's say we have some data from some search engine, maybe DuckDuckGo or some other search engine that maybe exports some of its data. I want to go through each row, and when I see search terms, let's say if let's say search term is rental cars in New York, maybe I want to just tokenize that list, and for each word in that search, I want to have a different row, because in my analysis, I'm almost like mapping them out into multiple rows, kind of like MapReduce, I suppose. So that we can implement by this version of the process row or fixed row. So we're taking a dictionary of text, and text type here, it's Unicode sensitive. So before I showed you byte string, which is just binary, and text would actually be Unicode aware, so depending on whether that's important or not. So anyways, I can just take that row. And here's, I guess, some more maybe Haskell syntax if you're not that familiar with it. And let's start here. So we have this where clause, which basically means in this sort of lexical scope, just perform all these things and make them available. So what I do here is, okay, I say M here is my row, and it's a dictionary. So I'm saying look up from the dictionary the column called terms. Let's say search terms. Okay, so now terms here, has essentially a string field that has the actual search performed by a user. Then I say, okay, take those terms and split on empty space, which essentially tokenizes that search. So if it had 3 words in it, I now have a list of 3 elements in pieces. Then I have this, I guess, value here, which basically says insert in a new column terms with, right, okay. I should have made this a little bit easier. It's not wrong, but it could have been a little more obvious. So what this is actually is, this is a function itself. Sorry for complicating a little bit. But so insert is a function that takes a key, a value, and then a dictionary, and then it inserts the value at key into the dictionary. Now by omitting the dictionary itself, I've made insert here a function. Sorry, this is carrying. It's slightly more advanced than I mean, I'm sure it's okay for most, but Essentially, this right here is a function that inserts into the dictionary each one of the terms that we just split. And then I just map over all the terms. And as a result, I basically get a list of dictionaries. But I guess the big picture is, even if this part, sorry, is a little more maybe unclear than I thought, it basically takes one row and it produces a bunch of rows, and each row containing only one word from that search term. And all of this you can do. And for me, one of the really nice things is, once you have all the rest set up, this is really in isolation. You can just make this function as complex as you want, and you don't have to touch any of the scaffolding, like going over the file and other parts. In other languages, typically you need to write a for loop and need to watch for the ends and everything. So, okay, so that was one maybe complication. Okay, so all that we talked about it's very trivial at this point to turn it into a command line program. So so far it might have been just like an empty exercise, I guess. But we could just with a few lines here, with Haskell programs, if you want to build an executable, you need to define a function main, and the compiler will just make sure that that function is called when you run the program. So all we do here is we get the arguments from I guess the program's environment, and then if it's given 4 arguments, so an input file, an output file, a separator, and a quotation character, and nothing else, then it will set the CSV settings to what the person just passed. And then it will actually process the file, and the process file being this function that we defined here. And then it will just say, I'm done. And this is actually, this is all there is to it. I mean, this actually will compile into an actual executable. You can run it. It's flexible enough that, I mean, for quite some time, I use something like this myself. It can become a first, I guess, step in a long routine of data analysis, where when you get a new file, you just pass it through this. It's like, it acts like a transforming filter, cleans up the fields, corrects the whole thing, and that's it. And it's actually pretty robust. It's an executable, so you don't have to worry about having like another language in the environment, and that's really all. Go ahead. No, not at all. Sorry, what's the... Oh, you're right. Yeah, I'm sorry. Yeah. You're right. I mean, this could be anything. There could have another like 10 arguments there. Yeah, good point. My bad. Yeah. I mean, there are libraries also to do this cleanly, but this was the most simple, I guess. Yes, sir.
Is this actually code you can run through the file?
Yep, absolutely.
If I'm in the little interpreter and I ask for the type of name, what does it return?
It will return IO unit. I mean, is that clear enough? Or? Yeah. So main is Yeah, sure. Okay. Anything else? No? Yes, sir.
How would you say the overall complexity of this code compared to the profile under the case for basically similar functionality, similar constraints, similar kinds of messy data?
I think at this level, it's probably about the same. It's possible maybe Python is maybe slightly less complex, just because you just don't have to worry about types at all. So at this scale, perhaps there might be a slight disadvantage to this. But I think what you gain from it, and this is maybe it's just me, maybe it's different for other people, but when I used Ruby and Python, I felt like there was a lot of sort of magic happening behind the scenes with a lot of the libraries. So if your use case fits exactly what the library is designed for, it works really well. But with an approach like this, it's both a really high-level language, but you still understand exactly what's going on. So if you need to make slight tweaks here and there, you get the power to actually make them, if that makes sense. Okay, sure. Sorry. This is constant space, yeah. Because of the library we're using. So the conduit library, it'll take care of all the scaffolding for you, but it'll read the input in chunks. It'll parse incrementally. As soon as one row is available, it'll be processed. It'll be written to disk, and then another row will. So I guess that's another maybe thing to note here. You don't worry about any of that. All of that is taken care of by the library, and sort of the higher order functions take advantage of that. You just give it a function to map over the input set, and not actually the whole sort of looping through the rows. Anything else? Okay. Okay, so I guess I'm almost done, but just wanted to show you maybe another level of sophistication here that we actually ended up doing, and we use this all the time. I personally use it all the time. So going back to these input files that you get for various reasons. So you might even have your own system, which in our case is the case. Let's say you collect a lot of data through some source, and you have 235 some odd columns in this data set, and you write it to some data store, and you extract from it occasionally, and you have a need to quickly process that, maybe put it into a SQL database or some other business analytics engine, and then do something with it. So it's really a big pain if you need to create a 235 column SQL table like 3 times a day. I mean, it takes forever if you do it manually, because you have to look at all the columns, figure out what their types need to be, and just kind of like guess them right. Even if you use a user sort of a GUI tool for it, it's still open the file, let it run through the first 10,000 rows, wait, then manually correct them. It's terrible. So the idea that I had after doing this a few times myself was, well, could we, I guess, write a program that would just go through this any given input file, really figure out what type each column should have, also make it optimal so that it's not wider than it needs to be, just kind of really comprehensively identify the input file, and then automatically generate the SQL code for it, and then actually give you the code. So you can just run it and you're done. The table is created for you. It's an exact fit for the data set you have at hand. And then maybe you could even import into that table automatically. So when you do all this, it really becomes you just type in some command line parameters, hit enter, and it does everything for you. So it's kind of a nice thing. And this kind of thing, I think, also lets me here talk about some of the more advanced and nicer features of Haskell. So in solving this problem, again, thinking about how would we tackle this, we said, okay, I guess we'll need a type that kind of tells, I guess represents an actual type in a SQL database. So we kept it simple. We typically don't need really fancy types. So we said, okay, I guess a field could be an integer, a double, a variable string, a text, kind of a blob, date, time, bool, or sort of blank, which basically means we don't know. It's some odd case that should never happen. So this one you define in Haskell, it's essentially a single type field that can take alternate sort of almost like subtypes. I don't know what I guess it's a sum type, but it basically has multiple constructors for the same type. It just keeps that information very, very cleanly for you. And again, I guess we will at some point need a function that just takes string, an unknown field, and will somehow figure out or make a best guess as to what field type it actually is. And if you had that, then you could give it any sort of value, and it'll guess what the type for you should be. And then if you have a full file, let's say 1,000,000 rows, I guess you'll have to go over every row there and kind of keep a dictionary of each column and what your best guess so far is as far as its type goes. And then again, in constant space, you iterate through this input file, maintaining this dictionary of what the types should be. And I guess here's one example of how that maintenance happens. So here's a function. Let's call it, I guess, update your guess. And in Haskell, you can actually have operators as functions, so it's kind of nice. It takes your old guess. So let's say before you thought the field would be an integer, and then your new guess based on the current row that you're looking at. And then it gives you an updated guess. And here you can, this is just a sort of a little extract from the whole function, but you can have a long list of cases where you say, okay, if I thought before that my field was an integer, and my new guess is also an integer, then that means my updated guess is still an integer with minimum and maximum values updated accordingly. However, if I ever get a text guess from my current row, let's say I have this file that has 3,000 really nicely laid out numbers, but then the next row actually has text in that field. Well, I no longer can say that column should be a number because there's at least one case that's not a number. So then you say whatever your old guess was, if you ever see a textual value in that field, then your guess forever now is a text. So you can, again, constant space stream through the file, and essentially at the end you'll get a dictionary where you know the type of each column. So we did this and turned it into a full-blown program. And there are some nice libraries that help you sort of have this documentation in command line. You have all this also in Python. But again, at least in my view, the design is really simple. By just So when I, for example, I recently ported a Cassandra driver from Python to Haskell, and in the Python version, it was a nightmare. I mean, to understand what it was doing with data marshalling, it had nested function definitions, and you had to have sort of dynamic scoping, almost in a sense. You had to really trace through. And I really, at the end, I couldn't even understand. After spending a couple hours, I couldn't know what the author actually tried to do. Whereas like with this kind of design, everything is very simple. Here are all the different values the field could take. It's all in one place. You can see it. Obviously, I have a function that identifies the field, and I have a function that sort of updates my guess. If you ever want to modify this, it's actually very trivial, which to me makes the end result very, very maintainable. And especially this part we use all the time. So now we say, let's say we have a 5 GB file. We say, okay, SQL import, table gen, input file, output file, look at the first 50,000 rows, do it for Postgres for us, and name the table this. We hit enter. I mean, this thing maybe runs for, I don't know, 30 seconds. And then it generates a very nice SQL file for us that contains the create table command, which again could be 300 lines long. And we just run it, and we're done. So very practical thing, nicely packaged up into an executable. You can run it anywhere you like. And has worked very, very well so far. So that's all I had. Hopefully it was at least mildly interesting. Any questions I can answer? Sorry. Sure.
What extent are those benefits specifically of Haskell or
I guess.
meaning would they translate to other languages or are they specifically with
Yeah. So I guess at a very high level, I think some of it will translate. So if you were to ask me, if you don't use Haskell, it's a common question, what else would you use? I would probably look at Scala or Clojure. Clojure is dynamically typed, which is probably my biggest concern with it, but I would try to look at it at least. And Scala is at least statically typed, but then it's impure. I think a lot of it, I mean, you'll get a lot of it by just, I mean, even before I started with Haskell, I used to use Ruby, and I would do like maps and reduces and injects all over the place. And after coming to Haskell, I was like, oh, okay, duh, like this is the real thing, and that was just kind of an adaptation of this. But I think it'll retain some. But some things here I think are pretty divisive, and some people really don't like it. But like purity, for example, for me it's a really big win because it really makes the programs really robust, really easy to reason with. You know that nothing crazy will happen in a pure function, and that I don't think there's any other language that really gives that to you. There are. There's a ton for sure. Right. I mean, yeah, you could always make the argument that you could use any language where you impose some kind of a human standard that says, okay, if this function name has this in it, we will never do I/O. But sure. But I guess nice thing with Haskell is once you're in that I/O monad, you're stuck. You just really can't get out of it unless you use unsafe perform I/O. But sorry.
This should not be read as an attack.
Sure. Brace for impact.
You realize the scope, the scale of your ambition. You're going up against Hawk. And Doug McElroy is on the Haskell Cafe Daily. Going up against Hawk. So I'm not an expert. Someday bring you with your weapon up against some guy who knows Hawk.
I just know the very basics in awk, so I wouldn't say. That's not how to parse sort of PS output.
But it doesn't have crash
At least awk syntax makes Haskell syntax look manageable.
Yeah!
Finally, we have that.
Somehow we have that. I like the tag. I love that. I don't do any Haskell, but the syntax is no whisper. Excuse me, what is this? What the hell is this thing?
You actually don't like the syntax? interesting because a lot of people, they might not like other parts of Haskell, but they like the syntax.
Right, yeah.
Interesting.
It looks like okay.
Hmm. Yes. Yes. Hmm. Hmm. Right. Yeah. So like Clojure has them, for example, or something like them, I think. But again, you don't have the type system in the first place, so it's a different beast. Oh. Mhm. Yeah, the question is, are you running into any performance issues or space leaks because it's non-strict and you might just accumulate thunks without evaluating them? The short answer in my experience is not really. I run into maybe a somewhat annoying case, maybe every 2 months or so, it seems. One of these weekends when I'm working on something, I'll run into an issue. But I do have the slight advantage of most of the work I do has to fit within like 100 milliseconds, sort of like a web request cycle. So you really don't have a lot of time to accumulate the thunks in the first place. But you'd be surprised. Typically, you don't run into them that often. But when you do run into them every now and then, yeah, you might spend a few hours just trying to figure out why you get the space leak where you really shouldn't. It's true. I mean, if I were to say the one thing that makes Haskell, or maybe two things, one is definitely space leaks. And the other is stack traces would be nice. I think if we had those two things, would be done. Stack traces. So you have a production environment, something crashes, you actually have no clue what crashed. You just get one message. Surprisingly, those crashes don't happen that often. That's the really interesting thing. I mean, I've been using Haskell in production for quite a long time now. It just, if you've done an okay job and it type checks and passes your test, you actually don't get crashes that often. But when they do happen, you're a little bit okay, I can tell that this function failed, but which call of that function, maybe that's a problem. Yes.
What kind of situation causes crashes?
In my experience, typically you made assumptions about your input data that don't hold. So a field is missing, or it doesn't have the format that you thought it would have. That's the most common case for me. The cases where like the network went down and database went down, and anyways, that it's fine. You notice that fairly easily. So it's data issues, I would say. Mm-hmm. Yeah. Oh, I mean, if you know that, I mean, I guess if you have that way of thinking, it's very, very easy to solve that problem. You just, the function you use, you just add a failure case. This kind of problem happens when you're kind of playing fast and loose with your programming. You're just making assumptions, calling, oh, I'm assuming this will never be, if it's a maybe value, so it will never have a nil in it. And you just assume that and keep moving. That's really bad practice. That's when it comes back to bite you. If you know that's the case, you just write a little combinator. It's a one-liner, and you say, okay, here's my own version of the lookup function from the dictionary. When it fails, it will properly report to me what dictionary it was reading from, what field it couldn't find, and what the found value was if it's badly formatted. So then you get this nice log in your errors, and you're done. No problem then. So it's not so bad. Okay. I think it's all yours, Gershom. Thank you, everyone.
Okay, let's see. I'm on the right, yeah.
Okay, so a couple quick announcements. You might have noted that 2 organizers of the group are giving the 2 talks tonight. We don't want it to be that way forever and ever in the future. So if you are interested in speaking, we want to have a good lineup. We actually do have the next talk lined up. Ed Kmet will be coming down from Boston on the 12th of December. He'll be giving his talk on his Lens library, which some people are really into. And it's a talk that went over well on the West Coast. It's going to be the full 2 hours. It is not going to be an intro talk. There will be parts, I think, that people will be able to take away things from in every direction, and I've been steering him towards making it more accessible. But it is not an intro talk, but it will be awesome, and Jay has his...
It is an intro talk.
Okay.
I'll tell you what, it's an intro. Patterns done right.
Okay, it will have introductory elements in it, I am informed. But anyway...
What do you think about the talk? An example of inference. Type it.
Okay, good, well, fine. In any case, so that is December 12th. We'll be putting the announcement soon. It'll be here at Pivotal again. We've got the space reserved. I'm really excited, and people are really excited about his library. So you've met Oz, you've met me. The other organizers of the group, in the back, we have Ryan Trinkle. Wave at nice people, Ryan. And next to him is Rick Meinrich. And then we have Doug, who is somewhere, right up front. And he'll say something afterwards, too. So we have a group of organizers here. So if you're interested in giving a talk, and it doesn't have to be an hour-long talk, it can be a 10-minute, here's a library I worked on, here's an experience report, here's a little project. If you're anything like that, we're going to try to schedule all sorts of different things. We want to make sure that everyone can present and that we can get variety. So please come talk to us or send an email to us through meetup.com or whatever, and we'll try to make that happen. I guess people can make their own announcements. I don't think Oz mentioned it. A number of the organizers actually are interested in meeting Haskell programmers and potentially employing Haskell programmers. Oz would like to meet you if you're interested in Haskell employment. I think Ryan is still looking as well. Doug has an announcement he'll make afterwards. So, when people say, why would I learn Haskell? What am I ever going to use it for? Well, now you can use it for employment. So this is really happening. All right. So let me get started with my talk now. So I actually happened to be in Boston for a Boston Haskell quite accidentally, and therefore I was able to give a demo version there. So I'm very happy because this is on Broadway, so it was quite literally an off-Broadway run of the talk. So okay, in the beginning was the command line. This is a really tiny screen, so I got to make this work. So this talk, wrong way. There we go. All right. So this talk. These slides are literate slides, so if you're not familiar with this, these are generated from a Haskell source file, and it's an executable source file, so I'll be executing the slides to give demos as I go, and we'll put the source code online, and there's an awesome program also written in Haskell by actually a philosophy professor at Berkeley, and the program is named Pandoc, and it reads like multiple varieties of markdowns, and it will translate them to multiple varieties of output. So this happens to be HTML5. It can also output PDF. It can output LaTeX. It's very powerful. So it's a really cool tool. And the best part is when you're giving a programming presentation. So you are guaranteed that all this code that you're seeing is the code we'll be running. There's a one-to-one correspondence. And I actually left up my call right there. Pandoc, using Markdown, literate Haskell. I'm actually compiling the slides. And on this side over here, I actually am compiling the slides as code as well. So, so just to show that off. Okay, so now let's just get into the talk. So I'm almost sorry I titled this Putting Cloud Haskell to Work, because immediately I got responses. I'm excited to see what you're using Cloud Haskell for in the real world. Oh, man. Maybe I shouldn't have said that. Because I actually, in a former job, we actually did use distributed Haskell computing. And we did real things involving managing pricing of various unsavory tranche products in a distributed fashion using Haskell. However, that is not what I'm doing now. And that was before Cloud Haskell existed. So we didn't use Cloud Haskell. Were we doing it now? I would. So this is going to be based on experience really using distributed Haskell for real work, but only based on playing with the new Cloud Haskell layer and implementation. So this is literate Haskell. So these are all the import statements of the many libraries I'm using in the course of this. Right, so there's nothing behind the curtain. All right. Let's talk about what Cloud Haskell is not, because I'm sure people have already heard many things that Haskell is not, that supposedly Haskell is, right? Haskell does not automatically memorize everything for you. Haskell does not mean that there will be no errors ever in anything you do, right? Haskell does not automatically parallelize every computation and run it on 1,000 cores without you telling it to, right? So we know those sorts of myths. If you're not as familiar with the distributed computing world, you might have heard and not known not to believe a lot of the same myths about Erlang, right? You know, Erlang will automatically parallelize everything for you. Erlang will, well, it'll always crash, but it'll always recover automatically, right? And you'll get 100% uptime and so on. So Cloud Haskell is not magic. It does not parallelize anything. It does not configure an architecture. It doesn't mean that things don't fail. And it doesn't tell you what to do if things do fail. What else doesn't it do? It doesn't have map reduce. There's no map function in Cloud Haskell. You have one in Haskell. You don't have a magic Cloud Haskell one. It doesn't have a reduce function. So it doesn't even give you a framework to do any of it. All right, so what is this thing good for, man? Ugh. Here we are. It's a substrate. So it is the essential pieces you need to build all this other stuff on top of. It is one layer of abstraction up, and it is the right layer that you need. And we'll talk about what that means. So it gives you ways to do this. And I've got another analogy here, right? People talk about plumbing. It's not even plumbing, but at least all your pipes, right, they're the same gauge. You don't have some British stuff, some American stuff, right? Not some of it's in metric, you know, that doesn't all fit. At least it all fits together. But then you still have to actually assemble everything. And so some of what I'll be talking about is what it means to assemble that stuff. I'll have some code examples. So what do I mean by distributed computation is different? Check my notes. Okay. Distributed computation is different because normally when we're talking about computation, a function is a function, right? And I mean, even if you have threads, you know, they're all running, you know, on the same, some thread in the multiprocessor. You don't worry too much about, you know, which processor in particular, which part of the core it's running on. So everything is very homogeneous. A function is just running somewhere. When you're talking about distributed computation, you're talking about different nodes really genuinely being different. So they have access to different resources. Some of them might be able to access a database nobody else can access. Some of them might actually be out in a field somewhere tied to a sensor. So the only guy that can tell you the temperature is the one that's actually hooked up to the thermometer. All right? So you have a much more of a notion of locality and resources and context for functions that you don't normally have. So where a function is executed matters as much as what function is executed. Along with that, also, not every resource has the same computational power. So even if they're the same in every other respect, you know, the fact that you're going to run it on, you know, a farm of computers, you know, in some data center as opposed to, you know, your laptop matters quite a bit as well. So that's another way in which you're thinking about resources a lot more carefully and locatedly. So when they started thinking about concurrent computation and distributed computation back in the day, so I don't know, maybe about half this room will know this story. I was very happy I gave this talk at Boston at MIT because it's an MIT story. And you had this character named Carl Hewitt at MIT. And he said, I'm coming up with something called the actor model. And people have probably heard of the actor model because, you know, Clojure talks about it, Akka and Scala talks about it, and so forth. He was actually inspired by Smalltalk. Not the Smalltalk we know today, but a very early version of Smalltalk that was very evolving. And Smalltalk had messages and passing, but it really actually didn't have concurrency. And he said, I want to think about what is the heart of what I want to do to capture concurrency. And he distilled it down, and he said, you have processing, storage, and communication. And an actor is something that has all three of those things, and the computation has all three of those things. As it so happened, a few other gentlemen, and I'll tell you their names in a bit, said, well, Carl, this is really, that's intriguing, but the language you've built up to express this is incomprehensible to us mortals. We have no idea what's going on. You know, we can't begin to tell you if it's actually a good idea because we don't know what it means. So they went ahead And they said, well, why don't we try to code it up and maybe we'll understand it. And they started writing and they started writing. And then they discovered something very interesting. They said, once we got the interpreter for our language working correctly, and the two folks were Sussman and Steele, who some people, maybe now you'll get where I'm going with this, and we played for it with a while, we were astonished to discover that program fragments in apply that implemented function application and actor invocation were identical. So it turned out that these were the same thing. And the language, all right, a lot of you probably know now, the language in which this happened, this was then what they called scheme. So scheme was initially an attempt to model Hewitt's actors. And then they realized that they'd actually just written the lambda calculus. And then they realized that this was a good idea. And someone pointed out to me that the reason people didn't make this connection sooner is scheme had tail call optimization, okay? And so if you think about every time you enter a function, you're descending a frame in the stack, then calling a function is a very imperative act, because you're sticking some context on, and you're going down, and you've got all this other context. But as soon as you have tail optimization, then it's really, it is literally exactly like sending a message, because you just fire it and forget. And if you're in a continuation passing transformed style, so everything just calls the next continuation, and it never returns, right? Like Charlie on the MTA, he never returns. When this is true, then you're actually living in actor land. And that's actually a pretty deep analogy, and it can take you pretty far when you're thinking about writing continuation style code. Now, actually, we'll get to it's not quite the same. Hewitt came back and said, actually, you're missing some key components, and they were. And, but, sorry, I'm just back on the detour. So many people may have seen some variant of this. All right, now this actually, they realized this first when they made this connection, right, from small talk, right, objects, the core of objects, to the actor calculus, all right, or the, to scheme, right? That's your direct connection from the core of actors, the core of objects, via actors to the core of lambda calculus. So, just let over lambda. So that's just a nice historical note. And what you need to add, that Hewitt pointed out, is you need locality. Is they actually, even in your CPS scheme, you still don't have some notion of sending things off to different places and communicating between different places. So you need some notion of locality and naming again. And scheme doesn't give you that unless you add primitives on top. Okay, so fast forward the story a bit. Another gentleman, actually his thesis was supervised by Carl Hewitt, and he is, this is going to kill me. I just had it on the tip of my tongue. He edited like scheme reports 2 through 5. Yeah, I know, it's killing me. And it's not on my notes because I screwed up. In any case, so a student of Hewitt's, who then went on to become a prominent guy, wrote the first denotational semantics, which we won't go into exactly what that means, but it's a way of giving meaning to a program. And he wrote the first denotational semantics for concurrent models of computation. And he did this in about 1980. And he used a construction that wasn't initially his, but he adopted it, called the power domain construction. And I'm not going to go into all the details, but the basic notion is, if you want to talk about what the meaning of a normal program is, it's very easy, right? You can just reduce each expression and see where it goes. I mean, I'm eclipsing 50 years of research, but basically you reduce each expression and sees where it goes. Now, if you're doing it with concurrent computation, what you actually do is you take the power domain like the power set. So you take every combination of every interleaving of every way these guys could all execute, and you just say they all happen at once. And so the meaning of the program is any of the possible things that can happen with any interleaving. So unlike a normal denotational semantics where you have confluence and you have one meaning, that's the true meaning of the program, now your program just has as many meanings as there are ways to run all the different clocks. So actors are good because, they can express just about anything, right? Given that. Actors are bad because they express just about anything. All right. The name will come to me. It's going to bug me the whole talk.
Is it Ray Dillinger?
No.
It's the other guy.
It's another guy.
There's only 2 I ever confused.
You're not talking about Sussman, right?
No. Anyway, okay. So Cloud Haskell right? It's the actor model, comes to Haskell via Erlang. It's lambdas in the cloud. And I didn't have time to make a little animation with a cloud and lambdas flying around, right? But it's a good image to have, okay? And one thing that's actually a metaphor I want to introduce, I guess before we get to the code part, is they didn't have, back in Hewitt's day, unfortunately, cell phones. Because if they did, they would have had the best metaphor for message passing ever. Because it is a text message, right? So I have my cell phone, I know your number, I can send you a text message. If you don't reply, maybe you didn't get it. Maybe you got it, but you were asleep, Maybe you got it and you don't like me and you're just blowing me off, right? I have no idea what happened. So we have the medium, we have the substrate, which is just fire and forget. But then, I have to wait for you to text me back, or maybe you never will. So we have to establish our own protocol on top of that substrate in order to have any meaningful communication. But we also see, with, flash mobs and whatever, so that, even though, all you can do is fire and forget, you can still organize 1,000 people to be in Times Square dressed up like Jedis or whatever. So clearly, there's enough power there, right? But you have to build protocols on top of it. And the analogy is good for thinking about the protocols you have to build, because it humanizes it. OK, so this is some stuff we ignore. This is how you get a Cloud Haskell program up and running. Again, we're just grabbing some arguments, just like Oz did from the command line. We're going to grab the host name of our machine. We're going to create what I call a distributed context. OK, so you actually have a whole hierarchy of things going on here. You have a notion of a backend, because they want this to be transport independent. So TCP/IP is a backend. But you could also do MPI, right, message passing type architectures. You can do, they actually have a backend for Azure. So you can do the Microsoft cloud. You could do the Amazon cloud. Nobody's written that yet, right? So you have some notion of a context. And the context is basically where you can find your friends, right? So you think of that as, a network, right? Of course, all the cell phone networks talk to each other, so it breaks down. But, it's like, friends and family, Verizon or whatever. OK. And then really what a context or a backend lets you do is you can create a node. So you can, buy a cell phone and hook it up to the provider. And then you can find out who else is out there. So you got a phone book. And so that's what we're going to do. We're going to find some peers in this context, get the phone book, and then we're going to call this run process function, which I'll get to, and I've got a couple variants of it. And we're just going to pass it who we are, so our cell phone and our phone book. And you have this hierarchy, actually, because on each backend you can have multiple nodes, right? So a backend is to a network, as a node is to a cell phone, as a process is to, well, actually, sorry. So nodes are funny. You don't really need them. They're just sort of living in the middle. A process is to a cell phone, or a person on a cell phone. A node is just this extra layer, so that if you want to have multiple totally different things using the Cloud Haskell transports, they can pop open their own nodes and do their own thing, is how I think of it. They don't really need to be there. We could build them on top of processes, but it just so happens in these things that your notion of locality is that you can have multiple sort of sources of nodes per project. I'm sorry I haven't worked the metaphor fully through. I'm sure if I had another week, I could really give you a bang-up one. So this is the most boring thing we can do. So if I call my process and I pass it boring, it's going to print, this is I/O within a process, and exit. Now what this demonstrates is that a process is, in monad I/O. So any action you can do in I/O, you can lift into a process and do within the process monad as well. I'm actually not even going to run it. It's too boring. But there it is. Now here's a good one. Volunteer. So now it says I'm going to listen. I'm going to expect a value of type unit, and when I get it, I'm going to be done. But until then, I'm going to hang out. We actually are never going to give this guy a value of type unit. This is just a way to keep the program running, so it'll stick around. Yeah, Jay, again.
The last one.
Yeah.
It looks like it's missing part of the definition of locality. So it's going to put that string with an end stop.
Mm-hmm.
Where's it going to put it?
It's going to put it in whoever happens to be actually running the process. This is happening wherever you are. Every process has to live someplace when you run it. So this is happening wherever the process lives.
So there's an output hopper, an output buffer, there's an screen.
Well, in I/O, we have this thing called put_strlen, and it just grabs, it grabs the output stream and pushes to it. So,
Right, but I'm just, the issue is locality.
yeah, well, this runs wherever that node happens to be running. We haven't gotten to anything distributed yet. This just shows you that you can still do I/O. And actually, if you do this, you're right. In the real code, you probably shouldn't be doing this because it'll be very hard to reason about where it's running. But that doesn't mean you can't do it. Just don't. OK, so this guy's volunteer. We're actually going to get a volunteer running. So he's going to discover his peers. It says peers discovered. It's sort of boring. There are no other peers. All right. Let's go back. So now this one is remote print. So this is locality here. So now, and I'll get into the grotty implementation details because what Cloud Haskell wants to be is not exactly what it is in the implementation. And so we can't do everything as nicely as we'd like. In theory, we actually are just firing off lambdas wherever they please. In practice, serializing functions is sort of hard, and we've got a hack at the moment instead of the right way to serialize functions. And I still don't even know what the real right way is. So we had to define print process at the top level, and I flipped past it earlier. So at the moment, the only functions you can serialize are those functions that you've actually defined at the top level and then called this sort of crufty template Haskell call on that says, I really want to make this a serializable thing. But that's just a mechanical transformation you can do to whatever code you need that just uglifies what you're doing. And it's a solvable problem, but the implementation doesn't solve it yet. So this is going to have a function called tellprint, which you pass a node ID to. And it will spawn on that node. So spawn says, you, other name, somewhere over there, right? You do this thing. And what it's going to do is it's called make closure. That's, again, template Haskell syntax, which is going to wrap up and make serializable this print process function, which is just printing whatever string you pass it. And it's going to pass it the string, hi there. All right? So now we're going to map tellprint over all the nodes that we found, and then we're going to return. So now we can go over here. This other guy here, he's going to open on a different port. We've got a volunteer on one side. We've got this guy on the other. This is, I think, called remote print. So he runs. He finds this guy. He says, you, execute this process. This other guy executes it. OK? So this demonstrates we actually have communication between different nodes. These are each running on different ports. They could be running on different machines on the same network. It just so happens that I have one machine plugged in. All right. This is something that's an example of where it's broken still. We need to fix this. I'm talking to people. I'm probably going to patch this, but this is irritating. This is to show you the work in progress. What happens if we pass it an int? Well, we shouldn't. It takes a string, clearly. The way make closure works, it forgets the type. It'll take anything that's serializable. So, whoops. This shouldn't happen. We need to fix this. It's not intractable. So I can call this. I'm not going to bother. And what will happen is, my analogy is it's like sending a text message in French to an Anglophone. The other process will get the message. It'll say, I don't understand this. What have you given? And it'll just throw it away. So nothing crashes, nothing core dumps, but it just means your code isn't doing what you'd expected that you could. You have a program that compiles but doesn't have as precise a meaning as you had hoped. All right. So this one shows that you can not just fire out and forget, but you can actually remotely invoke whole functions. Again, there's some ugliness, this function tdict and this make closure. I'll do the grotty implementation later. But so just sort of like squint and pretend those don't exist. And we're calling, again, do it is going to call, you give it a node, and it's going to call some process on the node. Some process takes two values, and it says, print out wherever you are, hey, I'm going to sum these values. Then return what you've done once you've summed them. So it's very exciting. That you can make this addition happen anywhere you want in the world. We map it over the nodes again, and then print what we've returned. Sum process. Is it sum? No, remote call. There we are. So you can see that, right? This guy now, he gets this new message. It says, print out what you're summing and send back the result. This guy over here, he's, remember, we've got a node here too. So he actually is listening to himself. And he also says, I'm summing them. And then so we print back both results we've gotten from both nodes. OK?
What code is executing the volunteer function? There's some process that's taking this exposure and then executing it, right?
This guy, yeah. Well, he's just sitting there, right? He's waiting. He's got one thing that's keeping him alive because he's waiting for a unit that he's never going to get. But that's just that one process. You still have a node. And so we can ship these closures over to that node. And that node is just sitting there waiting for messages and responding to them. And if that message says spawn a function, it spawns a function.
So as long as you have one process, you have a node, and then you can spawn processes on that node to create other processes.
Yeah, and in fact, you actually don't need that process. You could force the program to stay open without actually having to have like a little process there. I think it's a nice idiom to do that, because then you can shut it down if you really want to. But you don't have to do that. You could just, say forever wait or something. So there's other ways to do it, but that's one. All right, back here. Okay, so now we have this notion of a thing called a channel. And if you've used concurrent Haskell, you know normal concurrent Haskell has channels, right? So they're like a mailbox, and you can keep sending stuff onto the channel from any thread, and then you can read them off one by one. So we have the equivalent in distributed process, or Cloud Haskell. And the difference is you don't just have a channel. You have two ends of a channel, the send port and the receive port. And now the receive port can't be serialized. So you're not allowed to send it over the wire by definition, right? The only things we can send over the wire derive the serializable type class. So things like, a file handle, you can't really send it over the wire, right? Because, anything you can send over the wire, imagine you could also print to a file and read back a month later. So you can't have a file handle and then print it to a file and then read it back a month later, and you don't know where it is anymore. You can't have any transient thing and serialize it. Similarly, you can't have the receive end of a channel and send it over the wire, because you're getting the messages. This other guy isn't. How's that going to work? But you can send the send part of a channel over the wire, because that's just an address. That's just a mailbox. So here we go. So we're creating a new channel, and we got the send port and the receive port. This time we're going to spawn remotely chan process, which says expect a port, send it a message, then hang out a bit, thread delay. Now send it another message, thread delay, send it another message. All right. So what did we call that again? Remote chan. Oh, wrong side. So we can see, that was pretty fast. I could have put in larger thread delays. But you see that, again, we have two process nodes, this guy and that guy. Each of them spawns a process that sends back some messages over here, and then it prints them out. And you can see it's not happening this guy, then this guy. They're interleaved. The delays are happening. Everything is concurrent. So, obviously, none of this code is very exciting, but I hope it's showing you the primitives and sort of how you can do things with them. And then we'll get to a bit more interesting code later. Again, still nothing that really puts it to work, so I'm sorry for the title. But so do you have a question? Or? We're going to get there. All right. And in fact, we're getting there right now. So what's the first thing you do when you have some model of concurrency? You show you can implement everyone else's concurrency models on top of it. And especially this is important for actors and Cloud Haskell, because as I said, Cloud Haskell just, its semantics are just So what you really want to do is you want to have better, more well-behaved combinators that you can write on top of it. And so I have some sample code that builds a few different things. We don't have those libraries yet, but we can write those libraries. This is going to show, and I think we should. So, side note here, by the way, there's a really nice library for orchestrating concurrent processes called ORC, that came out of Galois, and Trevor Elliott and John Launchbury did it. And I realized that if we write this over distributed Haskell, we can call the package dork. So this must happen, okay? This must happen. Okay, so we're going to do a classical mvar. I did a whole bunch of these, so I might not do them all, because I got carried away, because it was fun. So this is your classical Haskell mvar, built on top of Cloud Haskell primitives. So it just shows some idioms. The first thing is we have these channels, and we expect typed messages. So we have to create types to represent our messages. Now, there's a lot of ways to derive binary. Typable we can derive for free from the compiler. Binary serialization is an external library. So you can use template Haskell or generics. There's a lot of ways to auto-derive binary. I'm taking my favorite simple route, which is if you have a new type wrapping something that is already an instance of a type class, you can use new type deriving or generalized new type deriving as is the extension, and then you can just pass through whatever the underlying instance is. So since process ID is binary, then a new type wrapping process ID is binary. So as long as we're not building our own ADTs, but just wrapping primitives, right, then all of these things we get binary and for free. And that just makes our lives a bit more pleasant for doing simple code. And so again, unit is binary, so wrapping unit is binary. And that's why we're not declaring just a new raw data type, but we're just wrapping unit, even though they're effectively the same, is to get that, that pass-through. So we're creating a new distributed mvar. So we've defined its vocabulary. Those are the messages we're passing. And a distributed mvar, unlike a real mvar, it can only hold serializable things. It can't hold anything on the planet. So we're going to back it by a real mvar, so we can cheat. You don't have to do this. You can write a distributed mvar just on Cloud Haskell primitives. But it's sort of a pain. Or you could wrap the good primitives with good semantics we already have in message passing interfaces, close over those, and then it's a lot easier. So that's the idiom I'm showing here. So forever just takes an action and does it forever. It's a monadic combinator, right? So we're going to spawn a local process that will forever, and I note it really is forever, unless you give an explicit exit. Like we can't do ref counting and figure out, if there's no references left, then we can garbage collect it. You have to build that as another layer. We're going to wait and receive, and then we use this match thing. So we can do pattern matching on, any different type you want, and it'll actually just test. Does it have the right type to be that? And so this is very Erlang-like. So if you get a take thing, we're going to lift the take mvar action and then send it back in the response. Now note that this guy, he's forever. So he gets a message, he does something, he gets a message, he does something. So if he gets a take message, what happens with take? You block until it's available. So if he was blocking, then he can't get any other messages. Like he can't get a put. And he's just going to sit there forever, and it's not a very good implementation. So we actually do another spawn local inside, all right? So that you make sure that everything that you're doing inside this loop is non-blocking. Similarly for put. You spawn it, and then you lift the action of putting it. Right? So if you don't know, by the way, an mvar is just a channel that only has one slot in it. So if it's full, you've got to wait to put something in. If it's empty, you've got to wait to pull something out. And that's basically the semantics. And you've got some sort of relatively fair choice. And then we return the mvar. So this is all we do to create it. It's not bad at all. You can see we're just wrapping its core operations in functions, and then providing the functions on channels, and then the underlying semantics preserved. So there's take. Now we're doing a couple of tricky things here. All right? So this is, I've got a dmvar. I'm living on another process on another computer on Mars. And I want to take this guy's mvar back on Earth. So I've got to get my own name to tell him where to send the information to. Then I'm going to send the message, but I'm going to link to it. And what linking does, it says, if that guy dies, then I want to get an exception too. All right? Because, what if I send the message to you and then, your phone is disconnected and you don't have service anymore? And I'll never get a message back. So with linking, we have a primitive that says, if that process dies, so we know for sure that we are never going to get a message back from him, then we're going to get an exception. That'll bubble up, so we don't just sit there waiting on a response forever. Then we wait for the response. Then we unlink, because now, we don't care. Now you can go off and die for all I care. I'm done with you. You're not my problem. And then we return the result. Put, exactly the same. Right? I don't think I need to walk through that. Right? Clear? Processes wrap state, messages interact with processes. So that's how you close over state in a distributed Haskell setting. So like I said, I got a bunch of these. I don't know how many I want to go through. Depends how we're doing on time. So this guy is a broadcast channel. So I explained earlier how your classic distributed Haskell channel, right, you can't serialize the send port, or the receive port, rather. But you can build one where you can serialize the receive port, right? And the same thing, we can actually build it on top of a normal channel, because you can duplicate listeners on a normal channel. So this C is from control.concurrent. It's the single process normal classic channel. So we spawn locally, we get our channel, forever we wait. If we get a subscribe request, then we duplicate the channel so that it's multiplexing what it's sending out, and then we spawn another guy that just links, and then forever reads out of that channel, and then sends it off to the guy who's subscribing, all right? And he's linked to that guy, so when the subscriber dies, he dies. So that's good. And then you can get an explicit die, too. Writing a chan is the same as sending a chan. Subscribing, I don't know how much detail people need or if they're comfortable with it. Oh, this is cute. I'm sorry, I forgot. There's actually something fun here. So when we subscribe to a channel, we can actually subscribe in different ways. So this guy here up, he's a gen. I say because he's generalized. And instead of actually just shoving it back into a channel on the receiver's end, we take an F, so some arbitrary function. And then, whenever we get the response back and we get a new update to the channel, instead of just necessarily doing any one thing with it, we just call this F on it. So, in this case, we are really just creating a new local channel and writing to it, and someone can listen on it. Here, we can do something else. Well, what if we have a commutative monoid? Because we don't really have a guarantee on the ordering of our messages. Then, every time instead of creating a new channel that we locally listen to, for every time we get a broadcast message, we have an IO ref, all right? So just a mutable variable. And then we apply our commutative monoidal operation with the new thing we get to that. And so now you've prohibited your end user from inspecting the order that the messages arrive because that order is meaningless. And so now by construction, you have an abstraction that doesn't let people think about the order that messages arrive, only what the value is. So you might want this if you have a progress counter, right? You have X% done. Everyone just sends back a 1. Your monoid is addition. And you just keep, adding them up until then you know what % done you are. And you can imagine building more complex things on top of that with more complex notions of distributed protocols. But that's fun. OK, so one of the other abstractions we have for doing concurrency and giving it good semantics is Tony Hoare's communicating sequential processes. I didn't do any PyCalculus, I'm sorry. I did one primitive, or not even a primitive, it's a higher level CSP function. But it's a common one because in Hoare-style processes, what you want to do is you want to have a notion of synchronization, and that's sort of core to it, is you don't just have everyone talking to everyone at once. What you do is you want to say, OK, everyone stop, wait until, are we all on the same page? Did our team have our scrum? All right, and then proceed. So we have a barrier. And a barrier is you enroll in it and say, OK, I'm enrolling in it. And when everyone who's enrolled in it has then synced to it, then everyone is released again. So you can have a bunch of guys that are all then waiting for everyone else to be ready, and then you proceed to the next stage. So it's a good way to stage things where you can, everyone can run around a while, and then you stop, and then everyone runs around again. There's a very simple barrier. You can build really clever, staged barriers and whatever. But one thing I was going to point out is we're doing all this stuff, and each message has a different type, and we're wrapping them with the new types. So it occurred to me while I was doing this, I didn't actually do it, but these are all just process IDs, right? So we could just pass a pair of string, process ID, and just match on equality on the string. And in fact, under the hood, that's what typable's doing, is it's comparing the thing. So you could do it directly if you felt like it. It's probably a bit safer this way because you can't make a typo, the compiler will tell you, but just to sort of, it's roughly equivalent. So there's a lot of levels of safety you can use depending on what you feel like. OK, there's a lot more going on here, so I don't know if I feel like walking through this all. All right, the basic notion, though, is you have a notion of who's enrolled. And it's got to have the set. So part of this was I wanted to show people sort of examples of how you think about more complicated concurrent things. Don't take any of this code and use it directly. I've only compiled it, not tested it, OK? So I've only, I haven't even proven it. So you have a triple here that is your core state. And that's going to be the number of guys that have enrolled in you, the number of guys that have synced with you thus far, and this thing that we're calling a monitor map. So mainly the interesting thing I wanted to show is we have this concept of monitoring. not sort of how the barrier works per se. And whenever someone enrolls in you, you also are adding them to the monitor map. But what you're doing is you're adding the monitor to the monitor map. So linking is very brutal. If that guy dies, I die. Monitoring says, if something interesting happens to that guy, send me a message, and then I'll decide what to do. So when you build up supervision trees and more complex types of starting and restarting and let it fail style Erlang things, then monitoring is your friend. And typically processes will link to their parents and parents will monitor their children. So in this case, if someone is enrolling in you, you don't want to die if they die, but you want to monitor them to think about what will happen if they die. And so we have a monitor map. If you get a sync, then we just we put that guy into the synced map as well. And then we check if the two maps match. If our enrolled and our synced are all the same, then we can actually release everybody. Otherwise, we just keep waiting. We signal that by whether or not our release list is full. And then if we're releasing everyone, that set is going to be full. And we're going to send clear, like go on ahead, all clear, to our entire release list. And if it's empty, then that's going to be empty, the release list. So that's how I just avoided having an extra Boolean flag there, just by having a full or empty set. You can resign, which is going to, if that's somewhere else, because you have two ways to resign. So if you explicitly say, I no longer want to be enrolled, we'll take you out of the enrolled set. And also the synced set, because otherwise things won't match. But also, if we get a notification that you've been killed or you've died, or that process somehow no longer is of this earth, then we will also automatically resign it. So that way, not everyone, everyone's waiting for Larry, but Larry overslept. You don't have that problem. All right, and then we return the barrier. All right, these pieces are simple, same as before. So on to the next concurrency thing. Just moving way into a different realm. Who here is familiar with Lamport clocks? Yes, Lamport clocks are like the poor man's vector clocks. Yes. All right, so maybe 3 people. All right, Lamport clocks are really cool. You have this notion in concurrency of, time doesn't work like you expect because everyone's watch gets out of sync, right? You can't trust any 2 CPU clocks are going to be the same. Maybe they're all syncing to the same time server, and even then, you don't know how long the messages take to get there. So you don't have an ordering on messages. So time gets very wonky. So this fellow named Leslie Lamport, who basically, if you find any cool concurrency algorithm, odds are he invented it, okay? But before he did that, he actually did physics. And his notion of a Lamport clock, which was one of the earliest real concurrency papers, was taken from, he realized the problems they were facing were a lot like thinking about special relativity, where you can't really think about a uniform notion of time, but you can think about a uniform notion of causal information. So things can't, you can't be your grandparent, but your times can still get out of sync, depending on where you are. So you have this very simple idea, actually, incredibly simple, called a logical clock. And a logical clock doesn't capture wall clock time, it just captures causation. And we'll create one. It's a number and a process. That's it. That's a Lamport clock. Done. All right. Now you know what a Lamport clock is. Go home. And it's got an update function. So whenever you see another Lamport clock, you take the greater of the 2 numbers, and then you add 1 to it. So so anything that you see could have had a causal effect on you. And your time is always greater than all of those other causations that have happened thus far. And what this gives you is not a total ordering, but a partial ordering on causality across a distributed system where you don't normally have a good way of reasoning about causality. Vector clocks are like this, but stronger and more complicated. So what are we going to do with our Lamport clock? We're going to wrap it up in a monad. This monad is going to be a transformer on top of our process monad. And now we're going to give Lamport semantics to everything that happens with all of our distributed processes. And so that's just a state transformer with a Lamport clock, and we wrap it up in a new type to make it opaque. Getting the clock, you just get it. Increment clock just adds 1 to it. You can cheat, but as long as you don't cheat with this and you only have a single process primitive at a time and not a whole bunch of interactions that are buried under lift, this we'll just increment the clock and send the message. So every time you take a meaningful action, you do that. If you're doing I/O, you actually don't have to increment the clock. This, I'm sure, is probably not right, because for something simple, it's actually notoriously complicated to actually make sure you're only incrementing where you need to be efficient and never not incrementing where you shouldn't and so forth, but the notion is all here. So now when we send, we get the clock, and then we just send it along with whatever we're sending. When we receive, we expect what we want to receive, but we also expect a clock. And then whatever the other clock we get from our other guy that we're receiving from, we update our clock by that one. So we're greater than the max of those two clocks. And then we return that clock too, so you can use it. You can hide the return, right? Just second fmap over that guy. And then you can use it like the normal expect. And this is, again, our semantics of a Lamport clock. If event A happens before event B, then I promise you that timestamp at event A will be less than timestamp at event B. And just by the logical rules of logic, if you take the timestamp at A and it is greater than B, then you know that A did not happen before B and could not possibly have caused B. Right? However, you've got a lot of in-between time. If timestamp of A is greater than B, then A didn't happen before B, but maybe it happened concurrently with B. You don't really know. And maybe there's no way of reasoning about which happened first, because they're just off in different worlds entirely. So it's a partial ordering, but that gives you a single thing. And what a vector clock does is it'll actually tell you when they're incomparable explicitly, but it has to do a lot of work to do that. And for 90% of the purposes that we need a Lamport clock or a vector clock, you can use a Lamport clock equally well. I was convinced that there's actually some actual uses for vector clocks, but I think they're sort of far between. For example, if you use REAC, a big selling point they have is, and if things don't reconcile, we give you back the unreconciled things and their vector clocks. Okay, great. Now they've made it your problem. What do I do with this? The tricky part, they just throw it back to you. So that, to me, is an example of there's maybe some structures, certain cute things called operational transforms, and others where that vector clock is useful. But very often, you're just going to have to throw up your hands when you know they don't reconcile, and those vector clocks won't help you. OK. All right, so we're almost done here. So now this is just, we're going to move off of, sorry, yeah, right?
Yeah, in a worst case scenario, we could actually have no temporal information.
Ray's asking me, in a worst case scenario, you could have no temporal information.
Like this worst case partial ordering when there's no ordering.
If nothing caused anything, then yeah, then you'll still get a total order. It just won't be it won't contain information because there is no information to contain. Sure.
I've used a model similar to this in the context of chatting and real-time logic. And you run into some
So one of the things, and we're going to get to this in the next slide when we talk about what we want to build on top of Cloud Haskell that's not there. One of the things that you have, for example, now in Erlang is they have a new model of traces for logging. And they use Lamport clocks under the covers. So that way, at least your log messages don't contain paradoxes. You don't have an insert logged into a database before you have the message sent out to insert it. And so that's a very useful tool. And that's the sort of thing that one can think about building on top of this too, to give those sorts of pieces. All right, so there we are. This is just a wish list. Some of these are things that I actually built for my old distributed system. Some of these are things that it would just be nice to have. We don't have a good notion of logging. There is a logging primitive now. It's pretty lame. It lets you choose one designated process to receive log messages, basically. What you really want are trees of logging that tie into trees of supervision, and you want filtering on top of that. So local processes can log a lot more configurably, right? You have your log levels. An error should filter up not just to the local process, but all the way up to the supervisor on that node, and then get sent back to the master supervisor. And if it's extreme warning, right, then you should make sure that it goes all the way back to the master supervisor, because that's something that you'll probably maybe want to pop up a big box or something on somebody's screen. So you need some notion of levels and filtering and trees of logging, because you might need different amounts of information in different contexts. And you might want to log them to different places. You can build that. It's not there. Supervision, like I said, you really don't have. You have monitoring, but we don't have a supervision tree. We don't actually have, and there's a project called Distributed Process Framework that exists on GitHub, and they've actually started committing to, that has some guys that know Erlang and know the OTP. So the OTP is the Open Telecom Platform, and this is another thing about Erlang. Everyone thinks that what makes Erlang great is the runtime. The runtime is nice. It works. The syntax is horrible. The language is okay. The OTP is brilliant. It is the result of a lot of pounding, of a lot of years, of a lot of different things. It's not even the cleanest thing to work with, but the reason Erlang is so robust is they built very robust frameworks as the result of a lot of mistakes and a lot of real-world experience. And that's what makes Erlang very robust. So we want to steal all those ideas. And the key among them is to have supervision trees where if any component fails, then you get a message above it, and we have that, we have monitoring. But then you have good behaviors for what to do. Do you restart it? Where do you restart it? Do you reserialize data? Do you have to throw away data because, this whole record is, hopeless? We don't have that. Out-of-process supervision is actually very important too, and we ran into this in the code I was doing, is you link to a big, ugly C library that does some awesome stuff. Now, that C library, if it has some memory problem and wants to stomp over your memory space, and run outside of its little sandbox, it can do that not just to that process, but to the entire runtime system, right? Because it's all one process to your Unix box. So, if you have an untrusted piece of code you're linking in, you don't just spawn a process to supervise it. You have to spawn a whole new system process and communicate with it over, a port or a pipe or something like that. And even then, if you're communicating and linked over a port or a pipe and not careful, it can corrupt the other end of the pipe so much that it'll take down the other guy talking to it on the other end of the pipe, which has happened to us too. So you need very paranoid out-of-process supervision. And then you need to make it seamless with your in-process supervision. We don't have that. You can do it, we don't have it. We don't have code swapping. Another myth about Erlang is that hot code swapping is awesome. I've had some people tell me that they've actually used it to some success. But the big guns will tell you they might use it in a development environment. In a production environment, if they want to roll out new code, they just have a lot of servers, and they just take them down one at a time, and it's okay because they've got a rack of 20 of them, and just roll the code to one after the other, just like you would in any other language. They will not do hot code swapping because it is just untrustworthy. So we don't need real hot code swapping, but we need a better way of rolling over processes, right? So if you guys have used Xmonad, which is the window manager written in Haskell, right? It's awesome, right? You can edit your Xmonad config and reload. And it doesn't use hot code swapping. What it'll do is it'll save every important piece of your state, write it out, relaunch the process, and then read it back in. All right? And you can build systems that do that in a very safe, transparent way on a large scale. And then that's how you actually do sort of incremental redeploys over a distributed cloud. We don't have that, though. The reason I put out of scope is I actually asked some of the guys now working on Cloud Haskell about this, since this was funded and by a number of different grants. I think they might be between grants. I don't know the latest. They're definitely looking for more grants to keep doing it. And they told me at this point what they're still doing in terms of commercial work and how they're building out this. That's just out of scope. I don't want it to be out of scope, but so that's something where other people jumping in would be great. Is they're not interested in that problem for what they're doing, the people that are now getting paid to develop it. So we want core monitoring functionality, pluggable, inspectable servers. Resumable computation would be very nice, so that when you get an error, it's not just that the supervisor knows what to do, but it can ask the user what to do on some master machine. Should I bother restarting this large job or whatever? You can model that stuff. It's just these libraries don't exist. And here we go. We want CSP, we want ORC, we want PyCalculus. We want all of those different sorts of primitives so people can pick the package of their choice and and implement it based on if they're more used to reasoning in one or another set of these things. One thing I will note, though, is a lot of these process calculi, and especially things, actually CSP is pretty bad at this too, but also PyCalculus and others, they really rely on synchronous messages. They're very much synchronous protocols. And so synchrony and asynchrony are dual. And I had some examples here. Once you have asynchronous calls, you can build a synchronous protocol on top. You can go the other way too. And some of the people involved in Erlang say they actually wish that they'd written it as a synchronous call language and put asynchrony on top, because it's just a real pain to go the other way. But you can do one or the other. But if you're in a big distributed context, it's probably better to be more asynchronous. And so a lot of these process calculi that really involve a lot of syncing, they're probably going to actually make your computations much more rigid, prone to failure, and so on, than if you're thinking in a more asynchronous manner. So the fact that you can implement them doesn't mean they'll all be a good fit for what you want to do. So I mentioned we want more algos. We want vector clocks. We want Paxos, just packaged up in a library so anybody can use. That's the advantage now, is we have one distributed protocol and layer. So if you write a Paxos, anybody can use it. You don't have to write it on top of your own protocol, and then if I want to use it, I've got to rip out your protocol and make it do something else. We have enough abstraction with Cloud Haskell that we can write it once and have the whole community use it. But somebody has to write it. OK, so I don't know how many of you guys know your punk rock history. This was from a punk rock zine in 1977. And it says, because you can't read the text at the top, it says, how do you play in a band, first and last in a series? And it says, this is a chord, this is another, this is a third, now form a band. All right? So I feel this is my version of that at this talk. We have abstraction, we have application, we have now added distribution. Now get excited, let's write some libraries together, and let's see what we can do with this. Let's talk. Doug, did you want to come up? Then, oh, do we have more questions, or? I think let's take them.
I was wondering if you look at the alternatives, there is a library called Columbus. I was just wondering if you've taken a look at it. Have you heard of Google?
Columbus is a different effort. It's not a. It's a map-reduce framework in parallel on a parallel grid.
But the underlying, it does provide an infrastructure for distributed channels, distributed variables.
I think it's not as robust or full-featured. It's much more particular. That's all I can say about it. I looked at it at some point, but I don't remember any details. Anyone else?
Is there a typical recommended book for learning Haskell?
For learning Haskell, yes. It's called Learn You a Haskell. It's online. That's the way to go. And then if you want to get a bit deeper into it, you pick up Real World Haskell. Both of them are also print books, but they're also free online. Real World is the O'Reilly book.
This is speculative, crazy. Plus.
From you, Jay?
So I think one can feel, even in the talk, there's tension. And the question is this just a case of style based on mistakes and you've always been talking about? Really? No, there's this distributed airline-like thing that, like the old system circa 1983 ran the United States telephone system. And you have those airline-type things. Then you have Haskell. That's tight, rigorous. Pieces fit together in a certain style that, before you compile it, you check it down to a resolution which other programming systems can't see at all. But I think in your talk, you begin to see that there's some difficulty. In other words, maybe the one is for things this big that fit in one thread, and then the other one, and this is not a knock against type systems, but there's more than one type system, right? And the type system of Haskell is a certain particular style, belongs to the whole family. But look, when you look at the airline, you look at the old, I forgot the name of the Unix system they used to use, and an OTP, and all that kind of stuff. Sure, there are type systems implicit there, right? There are things that have meaning with regard to the system, right? But they're not the same kind of thing.
I think this is a pub conversation, which leads me to the fact that we're running to the end of our time. Doug is going to direct us to the pub. Okay, but I wanted to ask first. I was told that one of the people who had worked on the initial Cloud Haskell paper was going to be here. Is that?
Hi, that's me.
Awesome.
I'm Epstein. I wrote the first version of Cloud Haskell.
So we're going to talk afterwards for sure, and then other people should say hi to Jeff and thank him for all his work to help build us these cool tools. So.
One question. I think I read that the Haskell serializing stuff will be going away in the future. Is that correct?
Oh, yeah, I didn't even do the, I promised I'd get back to it later, and I just didn't tell you how bad it was under the covers. Sorry, I know we have to get out of here. Really quickly, you have 3 versions of the semantics. You have what you really want, which is shipping things anywhere and serializing anything. You have the version that we pretend we have, which is an approximation, which is if you all have the same binary, you can, quote, serialize a function by serializing the pointer to that function, as long as every binary is the same. And then you have what we really have, which is that you use some template Haskell, so it generates a name and a location for the source code for this guy, and then you put another call that sticks it into a table. And then you just look it up in the table on the other end when you want to deserialize it, so you don't really use pointers. And you just have this indirection going on, which makes it really more of an actual RPC protocol than a actually serializing closures protocol. But it's better to think of it as a serializing closures protocol because it's closer to where we want to go. The GHC compiler guys have promised that at some point they're going to talk about how to put some real version of the semantics into the runtime. I don't think they've been doing actual work to make it happen yet. I think there's more discussions about the best way to do that I think people need to have. But in the meantime, this is totally usable. You just have to squint a bit at the template Haskell, and it's not too horrible. So there you go. Doug, yeah.
Two quick announcements. First of all, as we said, we have job opportunities. My former employer is looking for a Haskell developer. They do a significant amount of Haskell. There's also bits and pieces of Python and Java. If you're interested, I posted it to Haskell Cafe a couple times, but I'm re-announcing it here just in the interest of completeness. Talk to me. The company is Caramon Group. They're a small hedge fund. They have 6 people. They're my former employer, but I highly recommend them. They're just fantastic guys to work with. They're not snakes like some finance people. Anyway, if you're interested, talk to me. Second, we, as is common for New York meetups, are going to continue this discussion in an eating establishment nearby. The one we've chosen is called Central Bar. It's down on 9th Street, a couple of blocks east between, I think, 3rd and 4th or 2nd and 3rd. I and some of the other organizers will be headed there. We have room. They know we're coming. They can easily support like 50 people. And it should be a decent place to have conversations and do the nice networking that we also like to do. So thank you very much for coming. We really appreciate the turnout, and join us at Central Bar.
And see you next month.